In Chapter 2, we talked about elements and ions. Now we're going to move on to combining those elements into molecules and compounds. And eventually we're going to combine the molecules and compounds using chemical equations. As always, there's some suggested problems for you that are available at the back of the textbook. You can try these to make sure that you understand the concepts. When we're looking at compounds and molecules, we have to start connecting our elements together. We generally connect those elements by forming bonds. And there's two different types of bonds that we can form. We can form ionic bonds, which occur when we have a positive and a negative charge attracting to each other, so they form between ions. And we have covalent bonds, which happen when we share electrons. So in order to form an ionic bond, we have to transfer the electrons between our elements. And this happens when we have a cation and an anion. One will gain an electron, the other will lose an electron. So our anion gains, becomes negatively charged, our cation loses, becomes positively charged, and then those oppositely charged ions attract to each other. This happens generally when we have metal cations and non-metal anions. Covalent bonds happen between two atoms that share their electrons. And we know that it forms a covalent bond when we see non-metal atoms bonding together. So nonmetals share the electron between multiple atoms. Our sodium metal is going to form an ionic compound with chloride by losing an electron, becoming positively charged. Our chlorine is going to gain that electron that is lost by the sodium and become negatively charged. And then the positive charge of the sodium is attracted to the negative charge of the chlorine. We make sodium chloride. Now the interesting thing is that sodium metal is very reactive. When you put it in water, it'll form hydrogen gas and ignite. Chlorine gas is toxic if you breathe it. But when we form sodium chloride in this long-range repeating pattern, we get sodium chloride, which is table salt that we consume on a daily basis. Now please note that it is not just one positive sodium combining with one negative chloride, but it is a repeating pattern of sodium and chloride atoms making a large crystal structure. And ionic compounds form this large crystal structure. We still report their formula as the empirical formula, which we'll talk about in a little bit, 1 sodium and 1 chlorine, because that's the ratio that they combine in. Now when we represent chemical formulas, there's lots of different ways that we can represent them, and each one gives us differing amounts of information. The amount of information that we get depends on that type of formula. So we can start with the molecular formula. We use the elemental symbols and the number that tells us how many of each there are. So in this case, we have 1 carbon and 4 hydrogen. Because these are both nonmetals, this is a covalently bonded compound. If we move to the structural formula, we gain a little bit more information because now we see how the hydrogens are attached to the center carbon, but we still include those elemental symbols. When we go to the ball and stick model, now we have lost that elemental symbol, but we use colors to help us identify the element. Now we've started to gain some three-dimensional information. And carbon is black, hydrogen is typically white, nitrogen is blue, oxygen is red, and the halogens like chlorine is usually green. If we get to a space-filling model, now we start to see how those electron clouds are occupying three-dimensional space. We no longer see the bonds, but we start seeing how this fills volume in our structures. So as we mentioned, ionic compounds are reported as empirical formulas. Empirical formulas are the lowest terms of our chemical formula. So it tells us the relative number of atoms of each element in the compound. It doesn't tell us anything about how they're attached to each other or the shape, just the lowest terms. And all ionic compounds are reported as empirical. So for an example, we've got fluorspar, which is calcium chloride, 1 calcium with 2 chloride anions. When we get to molecular compounds, we can still write empirical formulas, but molecular compounds are not always written as empirical formulas. The molecular formula tells us the number of carbons, hydrogens, and oxygens that are attached to each other. The empirical formula is the lowest terms. So in this example, for our molecular formula, we would divide each of the subscripts by 2 in order to get our empirical formula. The reason we use empirical formulas because frequently this is the information we get from our chemical analysis. So looking at these different types of formulas give us different information. So if you notice, benzene and acetylene, they have the same empirical formula. When we move to the molecular formula, now we see that benzene is composed of 6 carbons and 6 hydrogens, whereas acetylene is 2 carbons and 2 hydrogens. The way that they're bonded together is given, or the structural formula gives us information about how these elements are bonded. So we see benzene is a ring. We have double bonds. So when there's 2 lines drawn, that is a double bond. When there's 1 line drawn, that is a single bond. When there's 3 lines, that is a triple bond. The ball and stick model gives us some additional information, and then finally the space filling. So benzene is frequently used as a cleaning molecule. It's really good at cleaning. Acetylene is used in cutting torches. Glucose, now we've added some oxygen into our chemical formula, and glucose is a type of sugar. And ammonia, you can see that we get nitrogen included. Your turn to practice writing molecular and empirical formulas. Pause the video and write the molecular and empirical formulas for these examples. For an ionic compound that has 2 aluminum ions for every 3 oxide ions, we're going to write the empirical formula because this is a metal and nonmetal, and so this would be an ionic compound that we would write the symbol for aluminum, and then a subscript telling us how many aluminum ions there are. So in this case, 2. We're going to write the symbol for oxygen and include a subscript for the number of oxygen ions. Arabinose is already given to us as the molecular formula. So to find the empirical formula, we would divide by a common factor. And so here we can divide by 5. So our empirical formula would be CH2O, dividing each of the subscripts by 5. Pyrimidine, now we've got a structural formula. So we want to count how many carbons there are. 4 carbons. We count hydrogens. 4 hydrogens. And we count nitrogens. And there are 2 nitrogens. Now when we write organic carbon-containing formulas, we start with carbon, then hydrogen, and then the other elements are written in alphabetical order. So our molecular formula for pyrimidine would be C4H4N2. To write our empirical formula, we would divide each subscript by 2. Get C2H2N. Ethylene glycol is shown to us in a ball and stick model. And now we have to use the colors to help us identify the formula. So carbon is black, and there are 2 carbons. Hydrogen is white, or grayish in this case. And there are 6 hydrogens. Oxygen is red, and there are 2 oxygen. Again, carbon first, then hydrogen, then any other element. We would divide our subscripts by 2, and so our empirical formula would be CH3O.